Hey, welcome guys. Yeah, so welcome to my video. Yeah, so now we go into the more deep finite group lecture. Yeah, so this video, let's talk about the proof of Sylow theorem. Okay, so Sylow theorem is probably the most beautiful theorem in the finite group theory. Okay, so let me just write down the statement. Okay, so let me just write down the statement of the Sylow theorem. Okay. So definition. So if G is finite group, and let's say we get some prime P, such that P to a K divides the order of G, and but P to a K plus 1 do not divide the order of G, and okay, so suppose you have a subgroup H satisfied. Suppose you have a subgroup H. Suppose you have a subgroup H with the order P to a K, such that P to a K divides G, but the P to a K plus 1 do not divide G. This H is called the Sylow P group. Okay, so Sylow group P group means that this P is the most largest power of P, such that the group G can have, right? Because my assumption is that PK divides G, but PK plus 1 do not divide G. Okay, so the famous theorem in called Sylow first theorem. The Sylow first theorem says that Sylow P group exists. This is the most beautiful part, I think. Okay, so if you go to the abstract algebra undergraduate textbook like Hurston, you will give you the 3 proofs. Okay, so but in this video I will not give the 3 proofs. Okay, so there are 2 kind of proof. Maybe in the next video I will give another proof, but in this video I use the mathematical. Let's see what we gonna do. Okay, so let's do the standard the counting proof. Okay, so before we do the counting proof, you should go to my previous video list about the group action, so that you will understand the proof. Okay, so let's quickly review the 3 lemma. I think we need 3 lemma to use. Okay, yeah, so before we do it, let's do the lemma. Okay, so lemma 1. Yeah, so this proof is somewhat it's the easiest one, I think, because it relies on 3 lemma. Okay, so suppose n is a p to alpha for some m, which m and alpha and mp are coprime. Then n choose p alpha. You can just write as this, right? So it's coprime to p. Coprime to p. Okay, this is the elementary number theory. So skip. Okay, then I skip the proof. Okay, so lemma 2 is also simple, right? Suppose you get some integer, and then you write x into the sum of the different integer, let's say x1 plus x2 as k, and the xi is integer. And if p, there is a prime number, divides x, then this p do not divide x, then there exists I, such that p do not divide xi. Okay, so this proof is trivial, because if this is not the case, that means each right-hand side, each x is divisible by p, then the left-hand side x will be divisible by p, which contradiction to my assumption. Okay, so I think these. Okay, so lemma 3 is also trivial. So suppose suppose you get some finite group G, and you take some subset J, which is a subset of G, and then you can define a set called Gj, which is X in the group G, such that Xj fixed J. Okay, so then then the number of the GJ as a set will less or equal to J. Okay, so for the proof is first notice that the GJ should be a group. Because let's say if so, you see identity in the GJ, because identity fix every element in the J. And also, if A fix J, if A belongs to GJ and B belongs to GJ, then AB will belongs to GJ. And also, if A belongs to GJ, that means AJ equals to J, right? So I can type J, you got A inverse J. So A inverse J is as a set still J, right? So which tell you that the GJ is a group. Okay, so once you know GJ is a group, then let's say you take J belongs to J, and you ask what is JGJ, right? So GJ is a group, right? So the order of JGJ will be GJ. Okay, but by definition, GJJ as a set must be a subset of J, right? Because every element of J will fix this, right? So then GJJ is a subset of J, so the number of the GJ will less or equal to J. Okay. So given any subsets of G, the number of the element in G which fix that subset must less or equal to J. Okay, so before we keep proving, let's review some basic of the group action. Right, so if you forget about it, it's fine. Right, so the group action means G act on X, and satisfy that the identity map on any S must be S, and the GHS must be GHS. Yeah, so this is called group action. And one can define a stabilizer. So this is the orbit. Orbit just of small s, meaning a GS where G belongs to G. So you just permute it. You permute it. This is the so-called orbit of X. I think I talked about this in the previous video. And then you can define a so-called stabilizer. So people call it stabilizer. Stabilizer. So stabilizer of the small s means that S is A. So it's a group G such that you fix S. Okay, so notice that G small s is a group. It's a subgroup of G. Okay, and the group action usually one count. So there are two count. Okay, so this is the this is the definition. Okay, and also notice that so we have two facts that you must remember. The first fact is that you can do the G quotient GS, right? Because it is a subgroup. Then the number of this is just the same as the orbit. Number of orbit. Okay, so this is also elementary proof. So I don't want to prove it because I think I proved it before. This is group action. And this is equivalence relation. Yeah, this is the equivalence relation. If so, the orbit S will separate the original, will separate the set into the different parts, right? So right, because you're S and you can separate into the theta, the orbit 1, orbit 2, up to orbit n, right? So once you prove this, then you can take S. So you know S is a sum of different orbits, right? So sum for different orbits. Okay, and you can easily check that the different orbit will not intersect each other. Okay, so this is easy to prove, right? Suppose let's see. So suppose this is orbit S1. So there's a S1 here, and then this is S2. And I guarantee that if S1, S2 are different orbits, then if there's a case that there's some of the element in orbit that meet together, then these two will meet together. Okay, so this is easy because if GS1 or some orbit of S1 right, match with HS2, right? Then the S1 will be G inverse HS2, right? And the S1, S2 will be the same orbit, right? So if there are indeed different orbit, then none of the element will intersect with each other. So this will partition S into the disjoint union, and each orbits, the number of each orbits, it's G over. So while writing this is stabilizer. So G divided by GS. Yeah, G divided by GS. Okay, and this is the sum of the orbit. Okay. Yeah, I think once we have this, then we are very close to a proof. Okay, so let's prove the first Sylow theorem. Okay, so the first Sylow theorem says that the Sylow P group exists. Okay, so let's say, so the idea is the proof. So the idea is that I want to prove that if G order is, let's say, P to the N to the M, right, and then P and M are coprime, I want to prove that there exists a subgroup H of G, which the order of H is just P to N, right? This is what we're going to prove. And right, so let's take this. Let's say take X, right? So X is a set which is a sub. Every element is a J, which is the order P to the N, and the subset of G. So it's not subgroup, subset. So H, and I collect all the X as a set. Okay, so each element of X is a subset of all the P to N. Okay, and now I can add the G account X into X, right? So this is a group action. So I need to tell you that what is the group action. So my group action is G, just account GJ. Okay, so yeah. Okay, so by the by this class equation, right? This is called class equation. So the number of X, and number of X will be just P to N times M choose P to N. So by the previous theorem that these two are coprime, to each other. Okay, so these two are coprime to P. Right, so P do not divide these, and this can be written as the sum over the different class. Right, sum over the different class. So sum over G divided by the some orbit. Say some orbit. Okay, some orbit of J. Okay. So by a lemma 2, these guys not divisible by P. Right, so that means right hand side must at least have one integer which is not divisible by P. Okay, so there exists J such that P do not divide G divided by GJ. Right, so remember that this GJ is the stabilizer, right? So this GJ by definition just G belongs to G where GJ is G. Okay, right? This is the normalized. The stabilizer. Okay, so but the problem is that the GJ is subgroup of G and the P do not divide this, right? So since G is P to N to M, right? So the GJ must be greater or equal to P to the N times something called M bar, right? And the M bar is divisible by M, right? But by the lemma 3, GJ is at most P to N, right? So combine these two, the only thing for GJ is P to N. Okay, so GJ is a subgroup, and then this is what we want, right? So this is the Sylow P group. Okay, so this is the first proof that you need 3 lemmas to give you this answer. Okay, so let's prove the second Sylow theorem. Okay, Sylow theorem has many applications. I think once we finish the main 3, I will talk about some further consequences in the future, in the next video. So second Sylow theorem. Okay, so second theorem says given a relation, so we'll talk about a relation of Sylow group G, right? So suppose so let me just theorem says that every Sylow P group, yeah. So this kind of group with largest prime power P, this is called Sylow P group. So every Sylow P group are conjugate to each other. Okay, so it means that if H1 and H2 are all Sylow group of G, then there exists a G belongs to G such that H1 GH1 and G inverse is H2. Okay, so proof. Yeah, so we can use the group action technique, right? So let's see what should we use? Okay, so okay, so let's consider set X, right? So this set X, yeah, so let's consider set X is basically G quotient H, right? So take H is a Sylow group of G, and the X is just G quotient H, right? So each element in the X is basically written as SH. X belongs to G. Okay, and so I need to give you a group action. Okay, so before I give the group action, let me just quickly mention let me just quickly compute the fix, what is the normalizer, right? So that it will not difficult. Okay, so let's right. So what is so and the G just act on X. So G act on X by just let's see. So G act on X by just for G times X act on X by just acting on G, right? So XH will just map into GSH. Okay, so this is the group action. My definition for group action. Okay, so let's compute a normalizer of S, right? So this S means the normalizer of this SH, right? So let's see. So we are going to compute, let's say Y belongs to this. Okay, so we want to compute the Y SH, which is SH, right? So which tell you that S inverse Y S H will be H. So SY S inverse Y S. Yeah, so okay, so let me just write. So you see Y is just let's see. Yeah, so this is G times G icon SH is just GSH. Right? So we want YSH to be SH. So we want to solve Y. We want to solve what? We want to solve yeah. So we can solve let me just write this. So we have this, right? So let's write S inverse Y S H is H. Okay, so S inverse Y S it just belongs to H, right? So Y belongs to SH S inverse. Okay, so you can easily check that GS is just SH S inverse. Okay, by just checking that yeah, so basically we just prove I write this. I just proved that the GS is subset of SHS inverse. But obviously that any element in the SHS inverse will still fix this. Right? So this is the orbit. Sorry, this is a stabilizer. Okay. So the same reason, the GH, right, the G quotient H by class equation. So remember that this guy do not have P do not divide this guy, right? Because G is a P to N and times M, right? And the M is compared to P, and the H is just P to N. So if you write them as different classes, right? There's no so in this case, right? There's no there will be P do not divide. So any class on this will not divide. There's always a fixed orbit such the fixed term which is do not divide. P do not divide that term. Okay. So let's imagine that so in the beginning that I just divide G on X goes to X, right? And then the X is G goes to H. So now let's say somebody give you another Sylow group. So give another Sylow group. let's say somebody give you another Sylow group K. Okay. So I do a restriction of the group action and change it into K econ X goes to X. Okay. So now it's just restricted the original group action to another subgroup of K, another subgroup of G. So what is the stabilizer? So original stabilizer is just a SHS inverse, right? So in this K term, your stabilizer is just original GS intersection with K. Okay, so now your stabilizer of GS is just is SH inverse intersection of K, or let me just write the GS tilde. Okay. Okay, so by this lemma, you can find by this lemma, so you can find the orbit. You can find a stabilizer, right? A stabilizer. Let's say this stabilizer is this. I call it S. Okay, so you can find a stabilizer such that G divided by this GS tilde is not divisible by P, right? But the problem is that if this is not divisible by P, then this GS tilde must be P to the because it must absorb all the P, right? It must absorb all the P. So it must be P to N, right? As we deducted before. So the same, but now this is GS intersection with K, right? And this K is also the P to N, right? Because it's a Sylow P group, right? So your GS intersection with K is the same as K, right? So the only case is K is a subset of GS. And the problem is that they are the same size, right? So K and GS are the same size, right? So GS must be K. Okay, so we just prove there exists S in G such that SHS inverse is K. So every two Sylow groups are conjugate to each other. Okay, so this is the second Sylow theorem. Okay, so let's prove the third Sylow theorem. Oh, and maybe there is a consequence that of the second Sylow theorem. Then I will talk in the next video. Okay. So this video just proves the main consequence. So the third Sylow theorem want to ask a question. So what is the number of Sylow P group? All right, so G finite group, and the G is P to the let's say M, and the PM is 1. There are greatest common divisor is 1. Okay, so the theorem says that the number of Sylow P group first is let's say this is NP. Okay, so the NP I think subset of is divisible, divides M. So M is divisible by NP, and the second is that NP is 1 mod P. Okay, so yeah, let's go to a proof. Okay, so probably this proof is the most difficult one. Okay, so consider omega, which is a set, which is all a Sylow P group. So H is a Sylow P group of P. H is a Sylow P group of G. And then you get G econ omega, right? So by conjugation. Okay, so yeah, by conjugation, so let's say this is H. So G, and I map it to G inverse. I use the words conjugation. Okay, and some very stupid guy will call, or very technical guy will call it inner automorphism. Okay, so yeah, hope you guys will not care about these terms. Yeah, so the technical term is called inner automorphism, but conjugation is much heavy. Okay, so first, right? So what? Let's ask a question. Well, what is the stabilizer? Right. So the stabilizer of H, let's say NH, is basically normalizer of H. In this group action contents should call it stabilizer, right? But in this terminology, I call it normalizer. So basically, it's all group G belongs to G such that the G inverse is H. Okay. So by definition, your class theorem tell you that the original group G quotient is N of H will be the same as what? The same as the orbit, right? But for H, the orbit for H is what? Oh, sorry, not just this, right? So G quotient N of H is a number, right? Is a number. Is an integer, right? So it's integer. Okay, and by definition, right? So the number of Sylow group NP is just what? It's just this, right? So okay, and let me see the reason. Yeah, so this is the number of Sylow P. This is the number of Sylow P group. So by the second theorem, okay, so this is the key point. Okay, so by the third theorem, right? By second theorem, these conjugation are transitive, right? So that means there's only one orbit because any two Sylow subgroups are conjugate to each other, right? So normalizer of any Sylow group H, N of H, there's only one class. So class equation of this omega, so there's only one class, right? So the number of Sylow group NP is just the remaining class of the number of the omega, right? So that means the set of omega is NP, and then there's only one case, only one orbit by second theorem, right? Because every Sylow P group are conjugate to each other. So this is just group G divisible by the normalizer, right? So N of H. So this is the stabilizer, but in this case, I call it normalizer. Okay. So this is NP, right? So G quotient this. Remember, and the N of H is larger than H, right? So all the P term will cancel, right? So the remaining term must be M bar, which M is divisible by M, right? So NP divisible by M. Oh, very, very difficult. Okay. Okay. So next is where we want to prove that NP is one mod P. Okay. So this is the very tricky one. Okay. So let me quickly get it. Okay. So remember that we just defined this. Right. So we define G and somebody gives you H and then want G inverse. Okay. So I restricted this group action into the subgroup H. Okay. I restrict this into a subgroup H. So let's say I restricted this to H econ omega by H inverse. Okay. So sorry, I should have GTO, right? Because it's omega. Every element in omega is a Sylow P group, right? So I choose a particular Sylow P group and doing a group action on all the set of different Sylow P groups. Okay, so this is the restriction. So remember that by a Sylow theorem, the second theorem tells me that the original G econ omega is transitive. So this guy is transitive. And then this guy probably not transitive. Because I restrict into H. So there's no guarantee that it must be transitive. Okay, so the problem is that it's not transitive, right? So by the class equation, so we can use by class equation. By class equation, the set is still omega, right? So omega, which is just NP, will be the sum of different class. Okay, but remember that there's only one. There's a guy which it is its own class, right? It's just H, right? Because H will fix itself, right? So H in this class is only he is his one orbit. Let me just, so H the orbit of H is just H, right? Because in this case, you use H to permute itself. So this guy must be 1 or something, right? 1 plus sum over the other cases, other class, which is H, right? Divisible by the sum or some normalized sum or stabilizer, right? So some stabilizer. And actually, I don't care. Okay. Let's say this is H prime, and this is just normalizer of H prime. Yeah, but that normalizer is restricted to H. Yeah, but who cares? Okay. So in order to remember that this H prime is what P to N, right? So in order to prove that NP is 1 mod P, the only thing we need to prove is that the orbits the only thing we need to prove is that only H has length of the orbit 1, length of the orbit 1. Okay, so if we prove this, then every guy here contains something which P to alpha, which is alpha is greater than 0. Then there will be remaining P here. Then once you divide P, then this is the only remaining. So NP will be 1 mod P. Okay. So we just need to show, need to show only H has at least one of the has the length of the orbit 1. Okay. Suppose there's H prime, which is a Sylow subgroup of G, right? So also P to N, and then which is normalized, which is length 1, right? So its orbit is length 1. That means your for all H, so your H prime, H inverse is H prime, right? For all H belongs to H. Okay, so but this will give you some strange contradiction. The reason is that so now your G is also P to N times something, right? So H prime. So now if you consider N of H prime, which is a set which normalize H. So let's say H tilde, H prime is H prime, H tilde. Right, so these guys are normal. The H prime is definitely the normal subgroup of H prime, and the N of H prime is the H prime is a subgroup of NH prime, and the NH prime is also a subgroup of G and greater than H prime, right? So, but in this case, right? In this case, you tell me that all the H belongs to H will fix this. So that means H is this, right? So we have this. But this guy is also prime to the sum past. The order is just prime power to something times something, right? And then N of H prime is less than G. So by the Sylow second theorem, if you forget about this G, and you use the second theorem, which tell you that these two are conjugate to each other, right? So by the second theorem, this H and H prime are conjugate to each other. And so the final keys here, and then they are conjugate to each other. So that means what? There exists. Let's say there exists some H belongs to H, such that what? So there exists, let's say alpha, right? I use alpha belongs to N of H prime, such that alpha H prime, alpha inverse is H. Okay, but alpha belongs to NH prime, right? So alpha will fix H prime, so H prime belongs to H. Okay, so this is a proof. Okay, so we prove H prime belongs to H, right? So that means the only guy which is length 1 up orbit is just H. So it means every term except for this one contains a prime power of something. So once you divide by P, then you will get disappear. Finally, you get the NP is 1 mod P. Okay, so this is the proof of Sylow theorem. And the next video, we talk about some consequence. And the next video, we talk about applications.